Hello, everyone. So, this is the second lecture about integers. So, I'm going to mostly talk about the integers. Some like related properties of integers. So, let's say that if we have n and m are two integers with the condition that n is less than m, then there exists a positive integer t such that m is n plus t. And with this, we start with some properties about the integers. So number one could be that we will talk about the principle of, well, ordering. And this says that every non-empty subset of Z hash, which is similar to Z plus positive integers, has a smallest, or you can say smallest element, i.e., if phi null state is not equals to S, or this S is not a non-empty, is not an empty set, then it is a subset of Z hash. Then there exists some X in S such that X is less than or equal to Y for all Y in S. Okay. So there, for every non-empty set of positive integers, positive integers has at least one smallest integer exist in every set. Now, let's say we have a subset S of positive integers. Then it has following properties: that n naught is in the S, i.e., there exists an element n naught inside the S, subset S. Number two property is, for all n greater than or equal to n naught, where n is the positive integer, if n is inside the set S, then n plus 1 is also inside the set S. And we show that now show that the set of all positive integers such that n is greater than or equal to n is in the set of positive integers such that n is greater than or equal to n naught is a subset of S. We show this. Let's take this one. So we will give the sketch of the proof here. Let's say, consider late that T denote the set and belongs to the positive integers, given that n is greater than or equal to n naught. And we suppose T is not a subset of S. Then there exists an element A inside T such that we know that A is not inside S. Now we will relate that there is another T1 be the set of all elements of T that are not in S. So we have T1 is T minus S. Since A is in T1, since A is in T and A is not in S, we have A is in T1. Thus, T1 is a non-empty subset of, thus, T1 is not phi and T1 is subset of. T1 is not phi non-empty subset of positive integers. Hence, by principle of well ordering, so we can say principle of well ordering, T1 has a smallest element M, smallest element M, then M is inside T and M is not inside S. Now we know that M is inside T, then M should be greater than or equal to N naught. And if M is N naught, then M should lie inside S because N naught is inside S, which is a contradiction. A contradiction. Thus, M is greater than N naught. This implies that M minus 1 is greater than or equal to N naught, and M minus 1 is greater than T. Now, M minus 1 is not inside T1, since M is smallest element of T1, so it cannot have more smallest element, and since M1 minus 1 is inside T, and M minus 1, sorry, there is M1, not M1, M minus 1. M minus 1 plus 1 is also inside S. Because M is inside S. So M minus 1 cannot be inside T1 because it is because M is the smallest element. And T1 does not contains those elements which are inside S. It only contains those elements which are inside T. So if M minus 1 is inside T, then M minus 1 plus 1 is also inside S, which is a contradiction. Hence, T is subset of S. Okay. Now, we have a theorem, and let's talk about that. Number is 1.21. It's the principle of mathematical induction. Statement is, let S be the subset of positive integers let n naught is inside S be the smallest element. Suppose S satisfies either of the following properties or conditions. Conditions. Number one, for all n greater than n naught, where n is the positive integer, if n is inside S, then so is n plus 1 is inside S. 2, for all m less than n, for n is positive integer, if m is inside S, then n is also inside S. And we can write a set which is for all those n inside the positive integers such that n is greater than or equal to n naught, which is a subset of S, which we have already proved. Now let's use this and then prove some college algebra or calculus course thing, which we called is that we have an example that sum of positive integers up to some n is equals to n into n plus 1 over 2, where n is greater than or equal to 1. Okay. Now, we show this statement using this principle of mathematical induction. So let's say proof or solution. Let's denote this by S of n. 1 plus 2 plus n is n into n plus 1 over 2, where n is greater than or equal to 1. This statement will be true if the left-hand side of the statement is equal to the right-hand side of this statement. So we will say that we know S is a set of those positive integers such that S of n is true. That is, the set of all non-negative integers n for which the statement S of n is true. We will show that S is the set of all positive integers. Now, we know for n is equals to 1, 1 is 1 into 1 plus 1 divided by 2. So S of 1 is true. Hence, 1 belongs to the set S. Now let n be an integer such that it is greater than 1 or even equals to, and suppose or assume S of n is true. S of n is true, which will show that n is inside S. We now show that S of n plus 1 is true. To do that, what we need to do, write S of n plus 1 as 1 plus 2 plus n plus 1, which is n plus 1 into n plus 2 over 2. Now consider the left-hand side. We will get 1 plus 2 plus n plus n plus 1 will be equals to, like up to here, it is n into n plus 1 over 2 plus n plus 1. We know S of n is true. So we will use that. We will use that and show and write n plus 1 into n plus 2 over 2. Hence, left-hand side is equals to right-hand side. And so S of n plus 1 is true. This shows n plus 1 also lies inside the set S. Hence, by principle of mathematical induction, set S for n is greater than or equal to 1. This proves our claim, which in turn show that indeed the sum of all positive integers up to n is equals to n into plus 1 over 2 when n is greater than or equal to 1. Now, we will write, to use this principle of mathematical induction, we will write the steps which we needed to prove this kind of situation or like problems. So proof by mathematical induction consists of 3 steps. A proof by mathematical induction consists 3 steps. Number 1, Step 1 is show that n naught is inside S, i.e. S of n naught is true for some n naught inside the positive integers. Step 2 is write the induction hypothesis. Which is n is an integer such that n is greater than or equal to n naught, and n is inside set S, i.e. S of n is true for some integer n such that n is greater than or equal to n naught, or you can say do same thing for some k. And then step 3 is show that n plus 1 is inside S, or you can say similar thing as S of n plus 1 is true. Then we have this example